A common problem that could occur with routing protocols is that of routing loops. Let's take a look at how routing loops occur. Here we have router A, B, and C. Notice the routing tables here we have listed the directly connected networks, network 1 and 2 on router A, out Ethernet 0 and serial 0. Router B here, networks 2 and network 3. Router C, networks 3 and 4. Just for fun, we'll call them Adam, Brenda, and Charlie. In Adam's routing table, Adam already knows about networks 1 and 2 because they're directly connected. However, using a routing protocol such as RIP, we'll just say we're using RIP. RIP sends updates every 30 seconds. RIP sends an update of its entire routing table, a copy of its entire routing table to other routers every 30 seconds. So, after 30 seconds goes by, Adam sends a copy of his routing table to Brenda. Brenda already knew about network 2, of course, but now Brenda learns about network 1 as well. Notice the metric that we have here for those directly connected networks. Since we're using RIP, we're using a metric of hop count. Remember, a hop count, or a hop, is how many routers that the packet would have to go through to arrive at the destination. So, from router A to network 1 and 2, we have to go through 0 hops, or 0 routers. Router B, Brenda, has now learned about network 1 from Adam via her serial 0 interface here. Okay, and notice now the metric that will be indicated will be 1 hop. In other words, to get to the 1 network, have to go through 1 router. At the same time, Adam learns from Brenda about network 3 and indicates that in the routing table here. Network 3 can be reached via the serial interface, and I would have to go 1 hop to get to the 3 network. Brenda and Charlie also exchange updates. Brenda learns about the 4 network from Charlie via the serial 1 interface there, and Charlie learns about the 2 network from Brenda via his serial 0 interface, going 1 hop as well. After another 30 seconds goes by, Brenda and Adam exchange updates again. This time, Brenda also informs Adam about the 4 network that's in the routing table here. So the 4 network is added here. Once again, serial 0. But notice it's 2 hops this time, because in order to get to that network, I'll add 1 hop to what Brenda told me here. In other words, to get to the 4 network, I have to go through 2 routers to get there. And Charlie learns from Brenda about the 1 network, and we'll add that to the routing table as well. Now, this is how routing tables converge. This is called convergence. So right now we have a fully converged network. All of our routers know about all of the routes. Say, for instance, now network 4 goes down. Charlie knows about the fact that network 4 has gone down, but Charlie's next update to Brenda is not due for another 25 seconds. However, in the meantime, Brenda has an update due in the next 5 seconds. So in 5 seconds, Brenda sends an update to Charlie, but Charlie's update won't be due for another 25 seconds. When network 4 goes down, here in the routing table, Charlie indicates that network 4 has instead of a metric of 0, Charlie says network 4 is down. But because Charlie's not going to speak up for the next 25 seconds, Charlie hears from Brenda that network 4 can be reached in 1 hop. So Charlie then thinks, well, if you can reach network 4 in 1 hop and you're 1 hop away from me, I must be able to reach it in 2 hops. So finally, After the 25 seconds goes by, Charlie says, okay, well, network 4 can be reached in 2 hops. Tells that to Brenda. Brenda says, well, you're the one that originally told me in the first place, so if you can reach it in 2 hops, I must be able to reach it in 3 hops. So then Brenda goes on and tells Adam, I can reach network 4 in 3 hops. Of course, Adam says, well, if you can reach it in 3 hops, I can reach it in 4 hops. And then after the next update goes by, Brenda sends an update to Charlie. Of course, by the way, when Charlie got that update from Brenda before, Charlie then also relearned the interface where that network would be from Brenda. So now Brenda sends an update and says, well, network 4 can be reached in 3 hops. Charlie says, well, I learned that from you via my serial 0 interface. So if you can reach it in 3 hops, I must be able to reach it in 4 hops. And this continues to go on and on and on and on. And this is a symptom called counting to infinity. Counting to infinity. Counting to infinity is a particular type of routing loop that occurs because of bad information that's being exchanged. Even though this network is down right here, router B, Brenda, is sending bad information, and so therefore this network will just continue to go on and propagate until infinity. That's called counting to infinity. Routing protocols have built-in mechanisms that, when implemented together, are all solutions to the routing loop issue. Let's take a look at a few of those now. One solution to the counting to infinity problem that we ran into here is defining a maximum. Instead of allowing this to propagate on and on and on, we define a maximum hop count for RIP. The maximum hop count is 15. That means if the metric ever reaches 16, that means that the network is considered to be unreachable. Unreachable. So that's defining a maximum. That keeps this counting to infinity problem from occurring. That's one solution. Now keep in mind, all of these solutions are implemented together. The second solution that we have is split horizon. Split horizon says it's never useful to send information or send a packet back out of an interface that it came in on. In other words, don't tell me what I just told you. Split horizon would address this counting to infinity issue by not allowing router B to send an update about network 4 back to the device where it originated. Originally, Charlie was the one that sent out an update about network 4. Split horizon does not allow information about network 4 to be sent back across that same interface. Another solution would be that of route poisoning. This is where when that network 4 goes down, immediately Charlie says the network is down and sends out a message that says this network is down. That's called route poisoning. Router B receives that route poison and says, okay, you say the network's down. I agree to that. And that's called a poison reverse. In other words, router C says, hey, network 4, bad news. Don't mess with network 4. Router B says, amen, brother. I agree. You say that network's down? I agree, that network's down. In the meantime, watch this. Even though router B, Brenda, says, yeah, that network's down, Brenda then turns around and puts in her routing table, possibly down. In other words, Brenda says, yeah, you're right, the network's down. But in my table, I'm going to say possibly down. Yeah, I don't know what issues are going on over there on that router C and all that. I don't know what's going on over there. But yeah, I'm just going to say it's possibly down. In the meantime, When this takes place, where I put possibly down in the routing table here, I start on router B what's called a hold down timer. That hold down timer begins to tick as soon as I have this possibly down state. As soon as I've received this route poison, I begin a hold down timer that allows the network to stabilize before reinstating that route. That way, even if the network comes back up and a message is received that that network's back up, I'm still going to keep possibly down in this routing table so that that network has the opportunity to stabilize. Because sometimes what happens is the network might go down, come back up, go back down, come back up. And instead of me having to reconverge my routing table each time and having to send out new updates to other routers each time this network flaps or goes up and down, I use the hold down timer to allow that network to stabilize before I reinstate any information or update any information about that network. So I keep possibly down in my routing table. I indicate a hold down timer. At the same time, I send a message to other routers indicating that that route has been poisoned. Over here, Adam also says network 4 is possibly down. And so now if a packet is destined for network 4 and it comes to Adam here, it comes to router A, Adam looks and says network 4, okay, serial 0, it's possibly down. Doesn't say it's down, so I'm still going to route the packet. The packet is routed to router B. Router B looks and says possibly down. Still send the packet. The packet is sent. It gets over to router C. Router C says, guys, I told you the network was down. And router C has to discard the packet. However, what's interesting is this. If the network comes back up, as I mentioned, the hold down timer is still going over here. So network comes back up. Charlie sends out a message and says, hey, glory, 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 everybody, be happy. Network 4 is back up. However, router B says, yeah, possibly down. Why does it say possibly down? Because my hold down timer has not expired. And so that way, in the meantime, if another packet is destined for that network over here, packet comes into A, says possibly down, still send the packet. B, possibly down, still send the packet. Now that packet gets to router C, and of course the network is back up again, and so therefore it'll arrive at the destination, even though these said possibly down. So that's a look at routing loops. A particular type of routing loop called counting to infinity occurs when bad information is exchanged between routers. A few solutions that routing protocols implement in order to address the routing loop issue include defining a maximum, split horizon, route poisoning, poison reverse, and hold down timers.